Hi there. So today I'd like to talk to you about density and pressure in fluids. So to introduce this chapter, the basic idea is that there's three common phases of matter: solid, liquids, and gases. Now, there's really many more than that. It's not that simple. There's others like plasmas, colloids, liquid crystals, but for now we're going to stick with the simple view that there's solids, liquids, and gases. So a solid has a definite shape and size. A liquid has a fixed volume, but it can be any shape. And a gas can be any shape and can also be easily compressed. Now, liquids and gases both flow, and there's some really similar physics equations that describe both gases and liquids. And so oftentimes those two types of materials get lumped together and they're called fluids. So, fluids are materials that can flow, and gases and liquids are both called fluids. Now, in order to go further into our exploration of fluids, their density and their pressure, we first have to define the term density. Now, this is something you've probably seen before, but the notation that we're going to use is that you have a mass density, and it's symbolized by the Greek letter rho, and then that's equal to the mass divided by the volume. So the density, rho, is equal to m divided by v. Now, the SI units of density are equal to kilograms per cubic meter. All right, so that's what we're going to go with most of the time. But you might also see density given in grams per cubic centimeter. That's a really common unit for density. And if you want to convert grams per cubic centimeter from grams per cubic centimeter to kilograms per cubic meter, you just multiply by 1,000. So you might have seen the density of water is about 1 gram per cubic centimeter, depending upon various things like the temperature and so on and so forth. But at atmospheric pressure for pure water, you've got a density of about 1 gram per centimeter cubed. And that translates to 1,000 kilograms per meter cubed. So just in case you're getting a little confused about the units or anything, let's do a quick review of the difference between mass, weight, and volume. Okay, so mass is a unit that's given in kilograms in the SI unit, and that's proportional to how many particles or how much stuff you actually have. Now, that's different from the weight of a substance, remember that. Weight is a force, and it's due to gravity's pull. And the formula for weight, the force, is equal to the mass times the gravitational acceleration constant here on planet Earth, little g, which is 9.8 meters per second squared. So this might be a review from your first physics class. Now, volume you might commonly see in measuring cups and things like that in liters, okay? But meters cubed is actually the SI unit, and that's how much space is taken up. Now, weight is mass times gravity, mg, so it would be the mass in kilograms times 9.8 meters per second squared. Remember that its force is the mass times an acceleration, and g is the acceleration due to gravity. And the SI unit of force is the Newton, which is a kilogram times a meter per second squared. So that's just a review for you of all those things, in case your mind went a little bit since the last time you had this material. Now, here's some densities of common substances at standard temperature and pressure. Standard temperature and pressure is defined as the freezing point of water, 0 degrees Celsius at sea level. So air has a density of about 1.3 kilograms per meter cubed. Now, that's a typical type of density for a gas at STP, roughly 1. You can think of roughly 1. Now, liquids have a density that's roughly a factor of 1,000 higher than that. So I think gases 1, liquids 1,000, and then solids 10,000-ish. Okay, so that's how I think of it in terms of the densities in kilograms per cubic meter. And that's kind of borne out by this table. You see that the density of aluminum is a few thousand kilograms per meter cubed to 2,700 actually, and then gold is 19,000 kilograms per cubic meter. So it varies, of course, depending upon the material, but that gives you a rough idea of what the densities are. Okay, so let's do a simple calculation and example problem. What's the approximate mass of air in a living room? That would be 5 meters by 4 meters by 3 meters. So this is a rectangular solid living room. So let's do that calculation. The volume would be the 5 meters times the 4 meters times the 3 meters. and 5 times 4 times 3 is 60. So the volume of the living room would be 60 cubic meters. Now the density is the mass divided by the volume, and we can use the density of air that was given in the previous chart, 1.3 kilograms per cubic meter, to solve for what mass of air would be in a living room of that size. So here you have 1.3 kilograms per cubic meter is equal to the mass m, which is the unknown here, divided by the volume, which is 60 cubic meters. Now you do a little simple algebra, a little cross multiplication to solve for the mass. You multiply both sides times 60. And then you end up with the mass is equal to 1.3 kilograms per meter cubed, which is your density, times the volume, 60 meters cubed. When you multiply those two things together, you get 78 kilograms, which is the mass of a big person. So you might not think of air as actually having that much mass to it, but it really does. All right, let's move on and define the pressure. A pressure is a force per unit area. So P here is the symbol that we'll use for pressure, and it's F over A, where F is the force and A is the area. Now F is going to be the magnitude of the force, and the pressure is only going to be exerted from the force that's perpendicular to the surface. In other words, if I push straight down on this book, I can change the pressure right on the surface, but if I push it to the side, it's just going to cause the book to slide sideways. So that doesn't significantly increase my pressure. It's only the perpendicular component of that force that changes the pressure that the book feels on its face. Pressure is a scalar, okay? So we're only going to talk about the pressure perpendicular to the surface, or the pressure due to the force perpendicular to the surface. And since pressure can be exerted equally on all sides of the container, it's going to be a scalar for us. The SI units of pressure are the Pascal, and 1 Pascal is 1 Newton per square meter. Now, you might think in terms of other units of pressure more easily than pascals. For example, we're used to thinking of the number of atmospheres of pressure that we experience. So 1 atmosphere of pressure is the pressure that everyone experiences at sea level. And 1 atmosphere of pressure is 101,300 pascals, or 101.3 kilopascals. Let's do an example with pressure that's not a gas before we move on to talking about gases and liquids or fluids. So, what's the pressure exerted on a floor by 1 pointed chair leg? Let's assume that the chair is 60 kilograms. It's a big, heavy chair, and it's on these little tiny legs, which is pretty typical for a lot of living room chairs. And the area of the bottom of those feet for the legs is 0.02 square centimeters. So let's compare that pressure to the pressure exerted on an elephant's foot. And let's say that the elephant is 1,500 kilograms and is standing on 1 foot. It's in a circus for whatever, doing a trick. So the foot area of the elephant is 800 square centimeters. So let's do that calculation and see what we find. So there's 4 legs holding up the weight of that chair, okay? That means that each leg supports 1/4 of the chair's weight if the weight's equally distributed through the legs, and we're going to assume it is. So the weight of the chair is mg, and then we're going to divide that by 4. So you have 60 kilograms times 9.8 meters per second squared divided by 4, and that gives you 147 newtons for the force that is perpendicular to the bottom of that chair leg. Now the pressure is equal to the force divided by the area. So that's 147 newtons divided by 0.02 square centimeters. Now since the newton is really related to the meter, we're going to have to convert those centimeters squared to meters squared. So 1 meter squared divided by 100 centimeters squared is going to be the conversion factor that we're using. Now bear in mind there, I'm not saying 1 meter squared is equal to 100 square centimeters. You've got to square everything. The conversion, which is 100 centimeters per meter, and the unit to get it to happen. That's why I put the square on the outside of the parenthesis there. Okay? So when I do that calculation, 147 divided by 0.02 and then times 100 squared, that's going to move it up to the top of the fraction there where you work it all out, you get 73,500,000 pascals, which seems like a lot, and it really is. And the reason for that, of course, is because the area is small. The area of the bottom of that chair leg is small, and that makes the pressure really high on one little tiny bit. This is why the bed of nails demo works, right? Have you ever seen somebody lying down on a bed of nails and the nails don't pierce the skin? That's because there's a lot of nails there, okay, which makes the pressure less on the skin from each one of the nails. Whereas if you're walking along and you step on one nail, it'll pierce right through your foot, right? So that's the kind of idea there. If you increase the area, the pressure decreases. Okay, so let's compare that to the pressure experienced by the elephant. Now the elephant has a lot more mass, right? Which means that the force of gravity is going to be larger, but the elephant's foot is also much bigger than the bottom of that chair. So if we plug those numbers in, we have the force is equal to 1,500 kilograms times 9.8 meters per second squared. That's our force. And then we're going to divide by the area, which is that 800 square centimeters. Now yet again, we've got to convert the square centimeters to square meters. We can do that by dividing by that 100 square centimeters conversion unit from the 800. And when we end up with our pressure, we end up with 183,750 pascals. Now that's still a lot of pressure, okay? It's over an atmosphere, but it's not the same pressure experienced by the chairlift. So it's crazier to think that an elephant standing on one leg has less pressure in its foot than a simple chair leg, where the chair only weighs 60 kilograms, or has a mass of 60 kilograms. But it is in fact a smaller pressure because of the difference in that area. So let's get back though to talking about pressure in terms of gases and liquids. So what causes pressure? And I know a lot of you are going to look at me, especially my students, you're going to look at me and say physics. Physics causes a lot of pressure. That's not the kind of pressure I mean. I mean pressure in a fluid. So what's the origin of the pressure in a fluid? Well, first of all, if you're talking about a gas, then the pressure in the gas, for example, the pressure that you experience inside of a balloon or a pressurized gas container, that comes from the little ideal gas molecules that are held within the container zipping around. See, ideal gas molecules, they're really not bound to one another. So one gas molecule and its neighbor don't really feel an attractive force that holds them together. What that means is that the gas is going to expand to fill the container that it's in. And of course, due to its temperature, it's going to zip around, bouncing off the walls of the container, okay? Now, each time that gas molecule collides with the walls of the container, it exerts a small impulse force due to its change in momentum, right? We talked about that in Physics 1. So all those little impulse forces, they're not large in and of themselves, but there's so many gas molecules inside the container that they're colliding with the container very frequently. So there's a lot of collisions with the walls of the container. And that causes the force that causes the pressure on the container's walls. All right? So that causes a lot of pressure. If you think about many moles of gas molecules inside the container, that's a lot of collisions per second, and that adds up very quickly to a measurable pressure. Now this is how gases and liquids are different, okay? We kind of lumped in this chapter gases and liquids together, and we talk about the similar physics, but there's also some very important differences that maybe we should highlight. So let's talk about this in terms of gases versus liquids. So gases and liquids are also different, even though both are considered fluids. An ideal gas molecule isn't attracted to its neighbors, but liquid molecules are attracted to their neighbors. If you think about surface tension in water and how water likes to stick together and be together, water molecules like to stick together, then you can understand what I mean by that, okay? So gases, they expand to fill whatever container they're in, and they can collide with the walls of that container, and that causes pressure. Liquids don't do that, okay? Liquids are actually approximated as incompressible. If you put a liquid within a container, it'll still just have whatever volume it has, and it sits and occupies only a small volume of the container that you put it in, as long as there's not much liquid there, right? So the liquids stick together, they don't expand to fill the whole container, and that means they don't exert all those collisions with the walls of the container like gases do, okay? And see, you can see that illustrated here. This astronaut was in space, and he was showing us what happened with a liquid in the space station. Okay, so he squirted the liquid, it was I think some kind of Kool-Aid or something, out of that straw, and it formed this little bubble. Okay, so there'd be no pressure, or basically no pressure, due to the collisions with the walls of the container from a liquid, because it's just sitting there stuck together, bound to itself. So it's different for gases versus liquids. However, if you're here on planet Earth, the weight of the fluid will still exert a force that causes a pressure on the walls of the container. And the deeper into the fluid that you go, the greater the weight of the water or whatever liquid it is above you, and hence the greater the pressure. Until, let's say that you're a scuba diver, if you go down really deep, you can feel a lot of pressure, several atmospheres of pressure, and it will only increase as you go deeper and deeper until it gets too dangerous to be down there, right? Now, however, in a regular chemistry lab beaker or a glass of water that you have sitting on your table or something like that, the difference in pressure between the top and the bottom of the container is really small because there's not a lot of fluid there. Now, another important thing to understand about pressure in fluids is that pressure is the same in every given direction in a fluid if you're at the same depth. Okay, so if you take this little tiny bit of water right here in the middle of this container, the pressure is going to be in all directions. Remember, it's a scalar, okay? Pressure is a scalar. But the force is being exerted in all directions on that little unit cube, the imaginary unit cube of fluid inside there, okay? So it's pushing equally in all directions in, okay? It has to push in all directions with equal strength if the fluid is at rest. Okay? If you had a pressure difference in one direction, the pressure was higher than the other, what would happen is the fluid would just flow, right? It would move. It would slosh around. So this is the case for what we call hydrostatic fluids, where the fluid's at rest, nothing's changing, it's in equilibrium. Also for a fluid at rest, there's not going to be any component of the force that's parallel to a solid surface. Yet again, if there were, then the fluid would just flow over that solid surface until the pressure was equalized. All right, so let's put some numbers to this. The pressure at some depth d below the surface of the liquid is due to the weight of the liquid above it. We already talked about that. But that's actually pretty easy to write in a calculation. What we can say is that the pressure at some depth d, which I'll call here little p, is equal to P naught, which is equal to the pressure at the surface of the container, or where the air meets the liquid, okay, so P naught, plus rho, the density of the fluid, g times g, the acceleration due to gravity, times d, the depth that you are within the fluid. So yet again, that's P is equal to P naught plus rho g d. Now this relationship is valid for any liquid whose density doesn't significantly change with depth, okay? So in other words, it's going to have to be something where you don't have an infinite amount or a very large amount of fluid above your head, okay? In that case, this approximation will break down. But it's valid for swimming pools, and it's valid up to certain depths in the ocean, and so on and so forth. Now, if the liquid is open to the atmosphere, like my water bottle container here, okay, it's just sitting in the container, then that P naught that we talked about is the pressure at the surface of the liquid. And lots of times in our physics problems, we're going to use atmospheric pressure as that P naught, okay? So P naught would then be 1 atmosphere, which is 1.013 times 10 to the 5th pascals. Now, you might see other units for pressure too. People have invented a lot of different devices to measure pressure over the years, and that gave rise to a lot of different pressure units. And this can be really confusing for students. Some of the ones that are out there are bars, centimeters of mercury, millimeters of mercury, torr. There's a lot of different units out there, okay? But pascals is the SI unit, so that's the one that's frequently used within your textbook. Now, the pressure that we're talking about, atmospheric pressure, or pressure when you're scuba diving as long as you don't go down too deep, that doesn't crush us. And the reason is, of course, it's in all directions, okay? And our cells maintain an internal pressure that balances it out. But I wouldn't try going too deep in the ocean, okay? So here's some of those pressure units that I was talking about. There's the atmosphere. We already talked about that one. The bar is a really common unit of pressure as well. And 1 atmosphere is roughly 1 bar. There's a little difference, as you can see here. 1 bar is actually 1 times 10 to the 5th newtons per meter squared, not 1.013, but they're really close. There's also pounds per square inch. That's the English unit that gets used a lot. In atmospheric pressure is 14.7 psi, or pounds per square inch. There's millimeters and centimeters of mercury. That comes from the way that they used to measure pressure. And then there's the torr. Okay, so the conversion units from pascals to all of those other pressure units are written here in this chart, and they're also in your textbook, so you can refer back to them at your leisure. So let's get familiar with one of those units of pressure by doing an example problem. Okay, you might have seen this kind of idea in cartoons. So let's say that there's a movie, a Tarzan cartoon movie, where Tarzan evades his captors by hiding underwater for a few minutes while he breathes through this long, thin reed or straw. You might have seen this. This is a really common trope in a lot of cartoons. So let's assume for a second that the maximum pressure difference his lungs can manage and still breathe is 85 millimeters of mercury. And then let's calculate the deepest that he could have been, okay? So what I mean by a pressure difference in this case is the pressure difference that he's experiencing by being under the fluid to atmospheric pressure, which is of course what's at the other end of that reed, okay? Okay, so first let's do a conversion of those units. So we have 85 millimeters of mercury, and we want to convert that to the SI unit, which is the Pascal. Referring back to that chart that I showed you earlier, the conversion for that is that 1 millimeter of mercury is 133 pascals. And so I'm going to multiply 85 times 133 to arrive at a pressure difference of 11,305 pascals that Tarzan can maintain. Okay? Now that's going to be equal to our pressure difference, which is the pressure that Tarzan experiences underneath the water minus atmospheric pressure. Okay, so P minus P naught will be 11,305. Now, I know from my equation that I introduced earlier, P is equal to P naught plus rho GD. So if I just subtract P naught from both sides of that equation, then I end up with P minus P naught is equal to rho GD. So I set that 11,305 pascals equal to rho GD, and I'm going to solve for D. Okay? I'm going to use the density of water, which is 1,000 kilograms per meter cubed. It might be different if it's salt water. Other things might change the density slightly, but that's a good estimate. Okay? So 1,000 kilograms per cubic meter times the acceleration due to gravity, 9.8 meters per second squared, and then that times D. And then I'm going to solve for D by dividing 11,305 by 1,000 times 9.8. When I do that, I end up with a depth of 1.15 meters, right? So we're talking 3-4 feet-ish of water above his head. That's not a lot, but that's the best Tarzan can do through that reed. So if you see something where Tarzan's breathing out of a really long pipe, it's not very realistic. Of course it is a cartoon. Anybody that's ever been snorkeling can tell you that when you breathe through a tube for a long time while you're snorkeling, looking at all the pretty fish, it really makes your lung muscles, or the muscles surrounding your lungs, tired after a while, okay? And that's just because it's a lot of work for you to maintain pulling in and out from that pressure difference, even though the depth that you're at in the water isn't very large, okay? So it's hard to breathe through a tube. It's hard on you. Scuba diving is actually easier in that way than snorkeling, okay? Now you might have other issues with scuba diving, but the snorkeling, you're having to pull through and you're having to make your muscles work to compensate for that pressure difference. Whereas in scuba diving, the tank is pressurized, and so you open the valve and breathe in, it almost shoots the air into your mouth. So it's kind of relaxing in comparison to snorkeling in that way. Now, it's important to understand that that equation that I cited, P is equal to P naught plus rho GD, assumes that the density of the fluid doesn't significantly change. Now, that's not the case for large bodies. In other words, our atmosphere, for example, violates the assumptions of that simple equation. And in fact, all fluids do really here on planet Earth. It's just that the difference isn't very much from the bottom to the top most of the time, and so we can ignore it, okay? In any fluid on Earth, the pull of gravity is going to cause a small change in density as you go up. Now, this isn't usually noticeable in like a regular lab container or a pool, or even some depth down into the seawater. But in Earth's atmosphere, we've got a lot of fluid above our heads, and it's a really big container, if you will. In that case, the changes in density as you go up in altitude can be quite significant, right? Atmospheric pressure is very different at sea level from how it is, say, up in the mountains somewhere, okay? The density is going to slowly go to zero as you move towards outer space. And that causes big differences in pressure as you change big differences in altitude. Okay, I hope you enjoyed that. We're going to pick up next time with how you read pressure off gauges and how lifts work, hydraulic lifts. So I'll see you next time.